The last video, I guess in the first video in the series, we looked at FMCW radars. So I thought I'll take some time in this video and introduce pulse radar systems. So we'll talk about, so this is the second video in this series where I will talk about pulse radars and especially matched filtering, which is a signal processing technique that they use for pulse radars. Okay, so we'll start with some basic intuition of what is a pulse radar. In some sense, a pulse radar is actually the most intuitive way that people think about, the general audience thinks about radar, for example. So for example, if you have, a transmitter and let's say a receiver RX, and I want to detect some object here, what do? You can send a very sharp pulse that goes out this way. So that travels out all the way to the object, hits the object, comes back. So when it comes back, it's delayed by some time t. Maybe I should draw it like this. It's delayed by some time t. So let's say this was where the original pulse was, and this is delayed by some time t. And what you can do is you can, by measuring this time t and it's using, propagation of electromagnetic waves in free space, you can say that the distance, let's call it L, just to be consistent with our previous video. So we know that speed is distance by time. I mean, speed is speed of light. So we know that L would then be c times time t. So this is basically the idea behind a simple radar system. But of course, this is too simplistic because it assumes, this pulse is very sharp. In reality, you may not be able to make such a sharp pulse. So, if the pulse is broad, what do you do? So then you can play some signal processing tricks, which we'll discuss in this video. But the basic idea is the same, where you send some pulse, you send some signal, and then you look for the signal in the response that you get back. And by looking at, what the delay is, you can get an idea of how far the target was. So to make it a little bit more realistic, what we can do is we assume we have some arbitrary pulse shape. So let's say this is time, and this is my pulse. So let me say, for example, the pulse has a shape that looks something like this. This is not a single peak. There are like two peaks in time. And this is the transmitted pulse. So you have our antenna, again, goes out. And let's say you have, for example, three targets. So one target here, and one target here. A simple model would be that, okay, each target sensor is, reflects the signal back, and the signal comes back. We have a receiver antenna here. So what do you expect to see? You would expect to see maybe something like this. So I'll make this the time, and let's call this R of t. Then you would expect to see three copies of this transmitted pulse. So let's see. Copy, paste. So let's say one of them here, and then another one here, and another one somewhere here. So that's sort of the received signal, right, from three targets. So what is the idea behind this sort of matched filter? Or if you have a more complicated pulse rather than a single impulse, how do we reconstruct the signal? So the idea is pretty simple. What you would do is you take the original pulse and you delay it. So for example, So you start from somewhere, let's say from out here, and you keep moving it along, and you see at which point you get a really good match. So for example, maybe, as you move this along, you see, boom, you get a really good match here, and then keep moving it along, and nothing's matching. Then you again get a really good match here, and then you keep moving it along, and we get another really good match here. So at every point when you move it along, you want to multiply this pulse signal with R of t, so that when you multiply them, in this case, you get a very strong match. And when it's somewhere in between or somewhere out here, when you multiply this signal and this signal, now you get zero basically, right? Because one of the signals is always zero. Even here, you would get a small signal, but there may be some situations, let's say maybe here, where since these two peaks are aligned, you may get a slightly larger signal, but the largest signal would be somewhere here, right? When it's perfectly aligned. So that is the idea behind match filtering, is where basically you take a template and you're correlating this template with your measured signal and seeing at which delay times do you get a good correlation. That's really what match filtering is. So now let's look at, let's say, such signal model, put this into some math and see how that looks. So it's the same idea really, just written out in equations. So the signal model for match filtering. Okay, so what do we have? We had, a received signal R of t. Let me actually write that here. So what we were doing is we had a received signal R of t, and we took our pulse, the transmitted signal P of t, which is this one here, and we kept delaying it by different amounts. So t minus tau, let's say, and we multiplied the two signals. And at each point you multiply them, you assign that, you multiply them, and then you add up the response so that you get a single number for each time, for each delayed tau. And then you assign that to some s of tau, right? And the addition here, once you multiply these two signals, you want to add them up so that addition can be written as an integral in dt. Right, so that's exactly in mathematical terms what I did back there when I slid the template across and did a multiplication. So you can rewrite this as, s of t, just changing t and tau, exchanging t and tau. This can be written as integral minus infinity to infinity, r of tau, p of tau minus t. So this is the mathematical expression for a correlation. For those of you who are familiar, hopefully you are familiar, because we'll be talking about more complicated math, I guess. But this is simply just r of t convolved with p of negative t, right? Because in the convolution it's p of t minus tau, whereas here, since we're doing correlation, it's minus t. So this is a symbol for convolution. And what we are doing here is correlation. So, I mean, hopefully you're familiar that, I can also write this as s of t is the inverse Fourier transform of the product Fourier transform of r of t times the Fourier transform of p of minus t. So this is a property of convolution or Fourier transforms, right? So a convolution operation is just product of the Fourier transform of each term. And then I'm taking the inverse Fourier transform to come back to the time domain. Right, so I can also write this as s of t is equal to the inverse Fourier transform of r of omega times p conjugate of omega. because of the negative sign here, you get a conjugate. It's another property of Fourier transforms. Okay, so that's essentially it. So this is what is called a match filter. And I guess this is called match filtering. And the match filter itself is this P of minus T. It's P star of minus T, but I'll just say P of minus T. This is the matched filter. It's pretty simple. You send a pulse, and then you look for the pulse in the received signal by template matching with the transmitted signal. Okay. Let's expand on this a little bit. So let's say I have, a single target, point target somewhere. So for a single target, at some distance L, what do I have? My received signal is just a delayed version of the transmitted signal, right? Because I only have a single target now. It has a time delay of 2L over C, and then comes back. Here I'm, of course, let me just mark this in red. I am ignoring the 1 over L square amplitude factor, amplitude dependence. For the most part, that doesn't really matter. So that's why you can kind of ignore it. But I just wanted to mention that. You can also put it in there. I mean, it doesn't really matter that much, but at least for conceptual and even the math, reconstruction, imaging, things like that, slowly varying amplitude functions don't make a difference. So we can ignore them. Okay, so if this is the received signal after some time delay, then what does the reconstructed signal look like, or the match filtered signal look like? So that is just the Fourier transform inverse of R of omega times P star of omega, which is what we derived up here. And now we know what R of omega is. R of omega is simply this is just the Fourier transform of R of t, which is equal to the Fourier transform of P of t minus 2L over C. And from properties, I mean, time translation properties of property of Fourier transform, you can write this as the Fourier transform inverse of P of omega times P star of omega. And this minus factor becomes now a frequency dependent term, an additional phase term, L omega over C. And that's just the property of Fourier transforms. So now we can write this as F inverse of modulus of P of omega whole square, e to the minus j to KL, where K, of course, is omega over C, a wave number. So what do we have? So essentially what we see is that the spectrum of your match filtered signal, which is the Fourier transform of the left-hand side, is just modulus of P of omega squared times e to the minus j to KL. A better box. No. So this is very nice because now we have a phase in the spectrum which is linear in L, right? So the phase is just 2KL. This 2KL phase will be very useful to us in the future when we want to do synthetic aperture radar or many of the algorithms that are popular for image processing, radar image processing. So that's just something to keep in mind. So what we can say now is that we can define this maybe write this is here. So this is P. All right, so what we can define is we can define a new term. So I will define F inverse of modulus of P of omega square as PSF of T, which stands for the point spread function. So if I do it this way, then we go back and look at this expression. What do I have? I end up with S of T. I'll just rewrite that. So I had S of T equal to F inverse of modulus of P of omega squared e to the minus J2 AL. And with this new definition, which I have of the point spread function, this is just nothing but the PSF of T minus 2L over C. Again, I'm using the time translation property of the Fourier transform. In this case, I guess the inverse Fourier transform. So what we see here is very important. So if I have a single target at a distance L, then the response of that target is essentially a shifted version, a time shifted version of the point spread function. So if I have to draw it, it would look something like this. Maybe something like this. Actually, let me redo that. I'm assuming this is what the PSF looks like. And this would be time shifted to exactly 2L over C in the time domain. This is my S of T. So that's why it's called the point spread function, in fact, because if you take a point target, it shows you what that looks like. It's only a function of the imaging system. It doesn't depend on what target you're imaging. It's essentially, you can also, I mean, some people also call this the Green's function. It's a very important concept in linear systems. So PSF is also called the Green's function. Although Green's function originates from a different place, the idea is sort of similar. The Green's function is, we have differential equations. If you want to find the solution, you apply, a delta function, and you look at what the solution to the differential equation is to a delta function. It's the same idea here. Here, instead of a differential equation, you have a system, a linear system, and you want to look at what the response of the system looks like to an impulse. This PSF actually is also the impulse response of your system, the imaging system. And this should be actually somewhat obvious if you studied, I guess, signals and systems. The impulse response is known to be the inverse Fourier transform of the power spectral density. And that's sort of what we see here as well, right? So this is the power spectral density. If you consider P of T as a system, as the matched filter, quote unquote, matched filter, then this is the power spectral density of your matched filter. And the inverse Fourier transform of that is just the impulse response of your system. So these are all the same ideas. So that's why I wanted to kind of mention them. Okay. So now that we looked at a single target, we can make it a little bit more complicated and look at a distributed target. So for a distributed target, I'm just going to be a little bit sloppy here. Mathematically, it matters, but for engineers, it doesn't matter. We just assume it is a collection of point targets, finite collection. So for all practical purposes, that's fine to do. So let's assume that there are n such target. Assume there are n such targets, n such point targets. Okay, with this assumption, the response after reflecting from all these point targets is just the summation of each of their responses. So it's a summation from n equal to 1 to n, sigma n, p of t minus to ln over c. Where ln is the distance to each target, distance to nth target, and rho n is the response of the nth target. So if it's a strong target, then sends a stronger signal back, response to the nth target. So I'm going to make another assumption here, and the assumption is that assume sigma n is independent of frequency. Which means that it doesn't have a frequency dependent, at least a fast varying frequency dependent response. Some targets actually do have that. For example, if a target is concave, it can have a frequency dependent response because of resonant modes. But we're just going to ignore that here and assume that, all targets are nice and point-like. If it does have a frequency response, there are ways of dealing with it. But in this tutorial, I guess I'm just going to skip that. For simplistic, or for, let me say, majority of real world targets, that's something you don't have to worry about too much. Okay. So with this assumption, then we can move on and take the Fourier transform. What does the Fourier transform of this look like? So that looks like R of omega is equal to sigma n equal to 1 to n. Sigma n, since, it's not frequency dependent, I can pull the Fourier transform in and just apply it on the p term. Again, using the property, I would get p of omega times e to the minus 2j omega ln over c. Okay, which again, going through the same steps, then s of omega would just be this times p of omega again, p star of omega. So then I can pull the p star in, and that would just give me sigma n modulus of p of omega square e to the minus j 2j omega ln over c. Okay. Again, taking the inverse Fourier transform of this would be summation n equal to 1 to n sigma n. And from the definition of PSF, this would just be PSF of t minus 2 ln over c. It's somewhat simple. All you have now is, if you have n targets, then the response from these n targets is just going to look like a summation of the point spread function responses from each of them, delayed by specific amounts. Again, here I've used some properties of Fourier transforms, fairly simple. You apply Fourier transform to this term, and for each of the term in the summation, you get one specific time delay. So let's look at maybe like a pictorial example of what this looks like. So let's say, my targets look something like this. This is with range L. Let's say I have a small target here, big one here. Right next to it, maybe I have one. Let's say I have one more here and one more here. So I'll just call this F of L. This is the response of each target. So maybe this is like sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. This is L1, L2, L3, L4, and L5. Okay. And if I transmit, let's say, a pulse that looks something like this, maybe similar to what we had earlier. This is time, AFT. And if I draw, let's say some time t, for each of them, I would get one responding pulse. And then I have to sum them up, right? So let's say for the first one, it looks the same, something like this. And then for this one, starts looking weird because you have two of them close by. And then the third one, something like this. Maybe the fourth one also looks something like this. So this is what my signal looks like. So then what you do is you pass this through the matched filter. So once you pass it through the matched filter, you have to look at the point spread function. So hopefully, point spread function should be much better than your transmitted pulse. So PSF of t versus t. So now so let me just rewrite. This one should be your R of t. And now I'm drawing your S of t. So this is after match filtering. So after match filtering now, if you go back down here, you should just get delayed sum of your point spread function. So one here, this, and one like this. So this is what the signal should look like. This is just sort of like an intuitive picture. Better way to do this would be to do like a MATLAB simulation, which I will do in a future video once I cover the theory of 2 or 3 different types of radars. I'll also do step frequency after this. And then for all three, maybe I'll just make one video on MATLAB implementations. So this idea, what is the idea here? The idea here is that even if you have a pulse that's not very sharp, it has all these side lobes, or it has, it's kind of broad, you can still get a response that looks like you're using a sharp pulse because the point spread function itself is sharp. And this idea is in general called pulse compression. And here we are doing it through matched filtering. Okay. Next, we'll do a quick derivation of the range resolution. So I think this should be section 2.3. So we saw here that this point spread function is not a delta function. It has some thickness, right? So in the FMCW video, there was a derivation we did for range resolution. It's very similar to that. So if you haven't seen that, maybe it's a good idea to look at that. But even if you haven't, it should be okay. So the idea of range resolution is that if I have two signals that are next to each other, or two targets that are right next to each other, then how close can they be so that you can still separate them? And what do you mean by separate? Is this enough, or do you want something that's like this, or do you need more? That is more of an arbitrary definition, at least in this case. When it's sampled, it's not that arbitrary, but in this case, we haven't done any sampling or anything like that. In FMCW, we covered that in more detail. But here I'll just go over the basic case. So, if you go back, it's obvious that, this range resolution depends on your point spread function, right? Because if the point spread function is thicker, then these pulses would all become too close to each other, these pulses. So since the point spread function is what matters here, that's all you really need to look at this range resolution. So let's just review. Point spread function is the inverse Fourier transform of the power spectral density of your match filter. Okay. So, to make a definition that is somewhat broad, what I'll do here is, what is typically done is that we assume that P of omega, or actually it doesn't matter really, mod P of omega square is rectangular. So what does that mean? That means that if you look at the frequency response or the power spectral density, we are assuming that this power spectral density is rectangular like that. This just simplifies things. And the width of this rectangle is the bandwidth. This is the bandwidth. Okay. So you assume P of omega square is rectangular with the bandwidth of delta omega, I'll call it. Okay. Then the PSF, which is the inverse Fourier transform of this, then the PSF, we know that Fourier transform of rectangular function is a sinc function. So then the PSF is a sinc. The derivation of this is covered in the FMCW video of, why a rectangular function gives you a sinc like this, but I won't repeat that here. And that sinc looks like this. It's a sinc of delta omega t over 2. Okay, so what does this mean? So this means that if I have two targets, or one target in this case, then the PSF would look like a sinc function. And the arbitrary sort of definition in this case for range resolution is that two targets are considered resolved if the second target lies in the first null of the first target's point spread function. So you want something that looks like this. That doesn't look very nice, but let me try that again. So maybe this is better. Okay. So what does that mean? So now these two targets are resolved. So this is in time, and this is, let's say, PSF of t. And we know that the sinc function has its first null, and the argument is equal to pi. So that means that delta omega times t over 2 is equal to pi. Okay. And we know that time and space, I guess time and length of the distance to the target are related. So, the time is 2L over C, right? Which means that if you want the space between these two, which is delta t, implies that the time difference is 2 times the space difference over C. Okay. Since we're looking at the difference here, we need delta omega times, actually this should be delta t divided by 2 equal to pi. So this should actually be delta t, with the notation I've used here, I guess. Right, because we're looking at this separation here. So that should be pi, which means that delta omega times 2 delta L over C over 2 equal to pi. This 2 and this 2 cancel. And then This pi cancels with the pi in here. This becomes 2f or 2 delta f. So anyway, after some simple algebra, you can show that the range resolution, which is the spacing between two targets in range, is C over 2 times delta f, which is C over 2 times the band. And this is exactly the same bandwidth that we got for FMCW. Same as FMCW. I mean, in reality, you may not be able to get this. So this is sort of the best case scenario, because in reality, you don't exactly know what the transmitted pulse was. Can be slightly different, and you don't have an exactly rectangular function. So this is sort of the number that's generally used. So if you want to design a system with a certain resolution, you know how much bandwidth you'll need. Okay, so in some sense, I guess we are pretty much done with pulse radars. It's easier a little bit because I haven't gone into too much depth. Easier, I guess, to understand than FMCW radars. So I'll end this with a basic discussion on the advantages and limitations of pulse radars. So advantages and limitations of pulse radars. Specifically here, I'm going to focus on mismatch filtering. Okay. So what is the big advantage of match filtering over FMCW processing? The big advantage is that you can show that a match filter guarantees to achieve the maximum possible SNR in the presence of additive white noise. It doesn't have to be Gaussian. I haven't obviously proved this, but that's not required, I guess, as an engineer. I just need to know that, okay, maybe it's required, I don't know. But it's just something to note, I guess, is that the match filter, because it is some sort of a filtering operation, right? Intuitively, it's a filtering operation. So it kind of, you can improve the signal to noise ratio compared to without doing match filtering. So if you just try to look at the pulses may be lost in noise, but once you apply the match filter, it can extract that out of the noise. So that's the big main advantage of using this match filtering approach. Another advantage is, compared to FMCW radars, you can do it for short and long range radars. So short to long range operation. So this is one of the drawbacks of FMCW, is that, if I have transmitted pulse like that, so this is time frequency plot again, is sort of referring to the previous video. For FMCW, you need the response to come very close to the transmitted pulse, because you're multiplying these two signals. I mean, if the response comes somewhere here, and if you multiply these two signals, you get 0 basically. But in this case, in pulse radars, even if you get a response much after the transmitted pulse has died out, you can still perform these operations because it's just a correlation. So in that sense, you can use it for radars that have very long range operation, from short to long. So you can look at very wide swaths, I guess, on the ground. That's one of the advantages. Another more subtle advantage is that the TX to RX leakages can be very low. Leakage can be basically 0. Right? Because what you can do is you can send a very fast chirp or a very fast pulse, and send a very fast pulse, and you just turn off the transmitter, and just listen to the receiver echoes, right? So in that case, Yeah, so when you turn off the transmitter, only listen to the receiver. There's no leakage between the transmitter and receiver. So, you can have very high sensitivity measurements. So that is another advantage. Okay. Now moving on to stuff that is not that good, I guess. Maybe one more kind of a double-edged sword is that you can use very versatile signals. So what does that mean? You can use different coding schemes, phase coding schemes, things like that. You can actually also use noise. You can send a noise signal, and then if you know exactly what the noise signal was, a pseudo-random noise signal, for example, that has very large bandwidth, you can just delay that and correlate that to the received signal and get a good response. The issue with this, however, is that, for complicated transmitted signals, if you don't exactly know what they are very well, very accurately, it's hard to design the right match filter, even as a digital filter. So that's why I say this is sort of a double-edged sword. So you can do complex coding schemes, but requires accurate knowledge of the TX signal. Okay. Now moving on to the real disadvantages, I would say. The big disadvantage, in my opinion, is bandwidth. Bandwidth and hence range resolution is limited. Why is that? Because, the one big reason why FMCW has become so popular now is that the mixing, you mix the TX and the RX signal in analog domain, right? It's an actual mixer. So once you mix the TX and RX signal, you essentially end up with an IF, that is only up to megahertz at most, few megahertz, right? So that's nice. It's a very low frequency signal. But in this case, you have to actually sample the received signal at the received signal's frequency itself. So for example, if I'm using a chirp signal in this case, so if I use a chirp for pulse radar and the chirp has a bandwidth, bandwidth from B1 to B2. So let's say this is the bandwidth delta omega, right? Then even with subsampling, I have to sample this at least at 2 times delta omega, right? So just to give you some numbers, I guess. So let's say, bandwidth is 15 gigahertz. How much range resolution can I get from this? So the range resolution is 3 into 10 to the power of 8 divided by 30 into 10 to the power of 9. So that's 1 centimeter. So for 1 centimeter range resolution, you need to sample the signal, the received signal, at least at 30 gigahertz. More realistically, maybe 60 gigahertz, right? 60 gigahertz sampling is impossible then, as far as I know, at least. So typically you're limited in bandwidth to hundreds of megahertz to maybe 1 to a couple of gigahertz. You can't go beyond that. So that's why the range resolution of pulse radar systems is very limited. And that's why for millimeter wave or for very high resolution radars, nobody uses pulse radars. Everyone just uses FMCW. Even though you have the limitation of, dealing with the signal processing is harder, because the location of the target is not only in phase, it's also in frequency. Whereas here it's only in the phase, which is very nice. So that makes the signal processing harder, but that's the only way you can get very high resolution systems. And the last thing I want to talk about, which I haven't talked about at all in this, is Doppler. So the Doppler processing for pulse systems is much more complicated than FMCW. So we saw that in FMCW, to get the range Doppler plot, you just need to take a 2D FFT, which is very fast. Whereas for pulse radars, to get Doppler signature, which I haven't really mentioned already, is one issue is that you assume that the received signal is just the linear summation of delayed copies of the transmitted signal. But if the target is moving, then the frequency of your transmitted signal shifts by the Doppler frequency, which means that now the match filter that you're using is not exactly correct, right? Because the signal now has changed. So to deal with that, what you can do is you can make like a filter bank with different match filters for different Doppler frequencies, and then try to assess what the different Doppler components of your signal are. But that is also not trivial. You need to look at something called the ambiguity function. I'm not going to go into details of that in this video, but what this ambiguity function is basically it looks at what if I send a signal and I get it back, and I pass it through different time delays and different Doppler frequencies, match filters with different time delay, different Doppler frequency, what does that cross correlation look like? For example, you may see a strong correlation even at a Doppler frequency and a delay that is not corresponding to the actual target's delay and Doppler frequency. So you have to look at this function when you're designing the pulse itself. And that's why Doppler processing is more complicated. So with that, I would like to sort of conclude this video on pulse radars. Hopefully it was a good introduction to pulse radar. I mean, this is not comprehensive. Obviously, this is just an introduction to the basic signal processing involved. Hopefully this gives you a good idea of what this whole thing is about. With this, I guess I can give you a short preview of what I plan to make videos on in the future. So I'll make one short video. So let me say future videos in the series. So I want to make one video on step frequency radars, which are actually a very practical and simple way of doing radars. Step frequency radars. And then what I'm more excited about actually is imaging algorithms. And there are many of these. So imaging algorithms for FMCW and pulsed/step frequency. What I'll actually show is that for pulsed and step frequency, they are very similar, but these two are quite different actually. These two groups, I would say. Pulsed and FMCW. So I'll talk about back projection or back propagation or delay and sum. They're basically almost the same thing. And then there is time domain correlation, omega k algorithm. Then there is range migration algorithm, pulse Doppler. There's so many. I mean, it's just everyone has a different name for these things. So anyways, and so on. So this is what I'm more excited about. Actually, this should be maybe from points 2 to 10. What is 10 in Roman? X. Yeah, points 2 to 10. So hopefully, that's somewhat interesting, and you can get a good understanding of radar imaging processing from these tutorials. So thank you.